Yeah, thank you. Thanks for coming. My name is Philip. I'm a protocol engineer at Circuit. Yeah, thanks also, Chris, for the introduction to rollups already. This means everyone that's still here must be actually interested, and I expect good questions later on. So yeah, let's just dive right in. How we just heard, how does a rollup basically work today and future, like Base, Circuit, Arbitrum. They all operate with centralized sequencers. Centralized sequencers have found product market fit, and they do actually scale Ethereum. And yeah, roughly they work in a way where a user sends the transactions and a centralized sequencer gives out a confirmation that it will include this block in the next batch. Then it will post this data to Ethereum L1, thereby achieving soft finality. And once this is achieved, the rollup architecture can propose a proof in case of ZK rollups, which we at Circuit are, and then we can prove the proposed output and thereby have a hard finality and let the user withdraw their funds again. Yeah, these centralized sequencers have helped achieve scalability on Ethereum. One thing that they are really good at is that they enable much faster UX. We have block times below 2 seconds, and with innovations such as Flashbox, which separate the block into 10 sub-blocks, again, even up to 200 milliseconds. The architecture is rather simple, as there is only like a single centralized entity, and you don't need to like replicate the L1 consensus layer on the L2, but rather you can focus on the execution layer and build out innovative features such as new opcodes. Also, they are less prone to like external MEV, as it's easily feasible to like, for example, achieve a private mempool, since you're just a centralized entity that's managing that. However, they pose some risks, as we already heard. They are more prone to censorship risks. One infamous example was at the rollup called Sonium at the beginning of the year, where they, a few days after launch day, they already started blacklisting some addresses of some meme coins, which had some obscene names. And yeah, in case of just an obscene meme coin name, you might argue, hey, that's totally fine, but it just shows you that generally there is still some trust me bro activity going on, that rollup nodes could in theory just like filter out your transactions on multiple layers, RPC within the network, or even just adding code to the sequencer. One mechanism that opposes this risk are forced transaction inclusions via the L1, which we, for example, have if you use the OP stack, one of the most popular rollup stacks. Then the user is able to enqueue the transaction through the L1, just like a user deposit transaction, and then the rollup is actually forced to build this, to include this transaction as the first transaction in the next L2 epoch. But this only helps if you're actively being censored. There's also another risk, is what if, for example, the government of a country says to a company, hey, shut down all the sequencer, we don't want this rollup nonsense anymore. Then your funds will still be locked on the smart contract in L1, but there is also mechanisms against that. For example, we in Circuit have also built an extra escape hatch that even if the sequencer goes offline completely for a predefined amount of time, you're still able to withdraw your funds from the L1 bridge contract, which, because in essence rollups are just bridges in L1, that's why they maintain the Ethereum security. Another issue is the lack of composability. As we already heard, optimistic rollups have a withdrawal period of 1 week. That's actually fast to speed up, because like these fraud-proof games have some like game theoretic issues, which I'm not gonna go further into. And then ZK rollups are a little bit better, but like for example, we have 4 hours of hard finality on Circuit. Others are slower, others are faster. Proving is progressing tremendously fast, but even then the question is this proving also economical for the rollup? So in essence, generally centralized sequencers do have an incentive to batch together data and batch together proofs and only post regularly on Ethereum L1. One thing that helps to mitigate this slow finality are cross-chain bridges. For example, there's protocols like Hop, Li-Fi, Stargate, Across, and many more. But actually, these are bridges. They are good. They help with the liquidity fragmentation in the happy case. But actually, like, don't be fooled by them too much. You first of all are relying on an external security mechanism if you're not using the canonical bridge, and particularly like in bank run cases or if a rollup gets hacked, they are not really helpful, because like what if all users wants to withdraw from a single rollup? These external bridges will not help you. And yeah, there's also an intent-based standard which aims to solve this type of liquidity fragmentation with ERC 7683. Finally, generally, if your aim was scalability, generally it sounds paradox to have a single point of failure, which we still do with the sequencer. Examples in the past, for example, that Base was offline for 33 minutes in August, or also Optimism in 2024 for more than 2 hours. Ironically, with the Base outage, it was a component. There was a component called OP Conductor on the OP stack, which aims to basically have a safe handover if one sequencer is like overloaded. Ironically, exactly this component failed and the sequencer still went down. And keep in mind that this downtime, I mean, banks have 2 days of downtime, but in this downtime, still users cannot transact, cannot move their funds, and essentially lose money. So how do we tackle this issue of centralized sequencing? The naive approach would be to just say, hey, we have decentralized L1, why don't we just replicate this on the L2? We have the necessary mechanisms, but keep in mind the goal of rollups was never to replicate the L1 consensus layer on L2. We can actually, since we are verifying our computations through, for example, a validity proof, we can abstract away a lot of the complexity. For example, we could just go against one of the issues of centralized sequencer, that they get all the revenue. You could say, hey, we could have proof of authority, we could have multiple sequencers, we can assign them different slots, and then maybe have the DAO decide what sequencer should get the sequencing right. That's one step to at least distribute the revenue, but it still is rather permissioned. Next step is that basically you would aim like, hey, why don't we have just a faster consensus layer on layer 2, for example, just some tenement-based or hotshot BFT-based consensus mechanism, and then we have a proof of stakes system on top of the L2, which decides who is allowed to post a new batch. But then again, I already voiced my concern that the idea should not be to make the L2 more complex than the L1. In regard of liveness, of course, the main pros of these type of approaches are revenue sharing and censorship resistance, but there's some other approaches, namely shared sequencing, which can also be interesting, in particular for the liquidity fragmentation, as they enable cross-chain transactions. Basically, in the case of shared sequencing, there's systems like Espresso and Astria, and then if the rollup opts in to be like part of the shared sequencer, basically different actors can bid for the sequencing right, and then if they have the sequencing right, they can basically even extract cross-chain MEV, build like the perfect cross-chain rollup block, and this would allow you, for example, to be sure that if you, for example, transact 1 ETH on Optimism and you want to also receive that 1 ETH in the same batch on Circuit, this would be possible with approaches like shared sequencing. But actually, let's go one step back again. These approaches that I just mentioned are kind of a complex layer on top of the layer 2. But why don't we just reuse our decentralized Ethereum L1 and use those as L2 sequencer? Well, that's the idea of based sequencing. A rollup is called based or L1 sequences if the L1 proposers decide basically what the next rollup batch is. This basically, by default, solves multiple issues that we voiced before. For example, that the L1 proposers collect L2 fees, and they would also be able to collect extracted value from these batches. And by default, since the Ethereum L1 is very decentralized, like we have a proof of stake system and we know who's going to propose the new block, you can basically give this task to the L1 proposers. But of course, and I get it, L1 proposers are also very opposed to too much change, and you cannot expect them to like just start building L2 batches, particularly for multiple rollups. There is 2 things to oppose this. First of all, an L1 validator only would have to like basically delegate that right, could get delegated to a so-called gateway, which then is building the L2 batch. It's actually very similar to what we already have on Ethereum today. The same happens with centralized block building, where basically the proposers let someone else design the perfect Ethereum block, and then in the end they just share the revenue. And if the proposer has not opted into the base rollup, you need some fallback mechanism. However, that's also possible. You just need basically a fallback sequencer, which then competes, basically just needs to have that L1 transactions in the same batch. So because you want the liveness for every 12 seconds, but you have to really ensure that this transaction is part of the block. Otherwise, the users have to wait for like 12 or 24 seconds. Yeah. So yeah, maybe a little bit easier illustration do we see here. Basically, in comparison to the centralized sequencers here, we would have like maybe just a public L2 mempool, and we have the L2 block builders, or the block proposers, which could in theory be the same instance as the L1 block builder, but in reality it would be more likely that the L1 block builder just coordinates with the L2 block proposers, and the block proposers give out send the batches to the L1. And yeah, the main difference to centralized sequencing here is that really the sequencing, basically who decides what the next batch is, this is all in the end up to the L1 validators. And yeah, you can see one error that I had here back from the L2 block proposer to the user, because one thing that we basically lost with this transition to base sequence is our fast block time. Because on L1 we have 12-second block time, and definitely we cannot go back to users waiting 12 seconds for L2 transactions, so that's not feasible. So the idea is here that, similar to centralized sequencers, since we know on Ethereum who the next proposer is going to be, we can still give out preconfirmations. What is a preconfirmation? A preconfirmation is basically a promise, a cryptographically signed promise to include the transaction in the next batch. That way users don't have to wait 12 seconds, but rather only a few hundred milliseconds. You get faster feedback, and yeah, but then the proposer has to make sure that this transaction is also part of the batch, which is one, it could be like a liveness fault if they fail to include the transaction, which in the beginning, as I told you, if you have a fallback sequencer, they really need to ensure that this transaction goes into the block. Otherwise, they'll get a configurable partial slashing penalty. And what would be even worse is like a safety fault, and this would be really bad if the proposers just, I don't know, arbitrarily execute transactions, and they will just give you wrong promises, and they would be then fully slashed. And also even the L1 proposer would also get partially slashed, because Ethereum wants to be like, you should be responsible as a L1 proposer to delegate to a good, to a benign L2 block builder. Yeah, so this is base sequencing, and then another term that's frequently heard is native rollups. So now, since we have fixed sequencing, we have to think, well, we still have multiple rollups. We have like 5 to 10 different rollups, which all are general purpose rollups. They all replicate the EVM, but then, for example, if there's an upgrade on Ethereum, like let's say there's a new opcode, a new transaction type, for example, just recently we had ERP7702, all the rollups have to do the same. They have to pull in upstream changes from Geth, they have to check the code, and then in case of a ZK rollup, they again have to fiddle with their circuits, have to check, hey, can we improve this? And now this got a lot easier with ZK VM migration and the progress there, but still, users still have to rely on each and every rollup that they basically did the correct implementation of the proof system. Well, this is aimed to be fixed with native rollups, where basically we introduce a new precompile on the L1, which basically checks if the L2 batch is valid by checking the execution trace and the state root before and after the output L2 batch that is output. And so by default, we get automatic upgrades on our rollups for the EVM. By default, it is, in quotation marks, bug-free, as it's basically this rollup is just an implementation of the EVM within the EVM. And also rollups would be finalized immediately with this, just within this single opcode. Yeah, but how do we actually verify that a rollup batch is valid? There's two execution models. One is re-execution, one is snark verification. Yeah, first of all, you can already see again how this opcode may look. And you have a state root before, basically on the bridge, which determines the state of the rollup, the state root after. Then you have an L2 execution trace of all the transactions, including state proofs. And now it's up to the L1 validator to execute this precompile and decide, hey, is this valid or not? And how do I do it? Like, the naive approach is just re-executing the whole trace. But this is kind of paradox, because our idea in the beginning was scalability. The only advantage of this, basically, that you could execute this in parallel, and then through that sort of get like an asynchronous scalability on the L1. But still, it's only a marginal improvement. The much bigger improvement comes if we, instead of re-executing everything on the L1, if we just have a snark proof, for example, if a ZKVM proof the L2 batch migration, and then we just verify this snark proof as a validator. Then the question again is, now as we have the snark proof to verify the rollup batch, how do we want to propagate this proof to the L1? There's two approaches. One would be basically off-chain through the peer-to-peer network. the advantage of this is that then each and every validator can decide for themselves what proof system do they want to rely on. Do they want to rely on succinct SP1 or RISC-0 or Nexus? It's up to them. If you have it on-chain, Ethereum would lose their neutrality and they would have to decide, hey, we rely on this proof system. And yeah, that's probably not beneficial in these early stages of these provers. So yeah, by default, we also get proof diversity on the L1. However, this of course is all based on a very idealistic assumption that A, there is someone actually willing to prove all of these rollup batches, and then B, if we have proof diversity, they would even have to prove the batch with multiple different provers. And yeah, then even the question is who pays for all of these proofs. You could even, there's attacks on this also that you, for example, could design DA batches which make the next person that has to prove it very expensive. So yeah, these are the developments of based and native rollups. And the next steps are, as I already said, the provers need to still get much cheaper and much faster. At the moment, I think we are at like a state where like 95% of L1 blocks can already be proven in real time, which is a great improvement, but basically we need 99.99%, and we need this for multiple proof systems. Then we do need still improved infrastructure and more experience, for example, for based rollups. These pre-confirmation systems through a gateway are still new, and for example, one EIP that's targeted to be included in the next Ethereum upgrade is EIP 7917, which is called deterministic proposer look ahead. Basically, this makes it much easier to make pre-confirmations a reality, because if you know exactly who's going to propose the next L1 block, it's much easier for you to co-locate with this proposer, and you can have a gateway, for example, in the same geographic region. At the moment, actually, proposer look ahead is almost deterministic, but it's determined at the beginning of the L1 epoch. But yeah, we target to make this completely deterministic with the next Ethereum upgrade. Then one big aspect which is not talked about enough is L1 finality. For example, particularly with based rollups, you have to take into account that at the moment it takes a full L1 Ethereum epoch, which is about 6 to 12 minutes, to determine if the block is actually finalized, if it's going to stay there. And there's reorgs. And reorgs are actually very severe for based rollups, because as long as the block is not final, you don't know if the transaction could still get thrown out of a batch. And also, as long as you don't know that it's final, you can make two choices. Either, okay, I'm already going to start proving the batch, even though I'm not sure that it's going to be finalized. But then, of course, you waste a lot of resources, or you have to just wait these minutes before you can start proving. And this, in the end, again, impacts the interoperability of these rollups then. And then, yeah, finally, there are some economic questions that I didn't even get to touch yet. And it's also a question like, how would you price such a new execute precompile? Would you have a dynamic fee for these enshrined rollups? And yeah, who's going to prove all of this? These are still open questions. Yeah, if this was interesting to you, there's a number of resources, particularly on the ETH Research Forum. And yeah, other than that, thank you for your attention and happy to take any questions.